After studying this module, you shall be able to learn about different aspects of bonding involved in supramolecular chemistry, know about non-covalent interactions, and understand the concept and energies associated with different classes of non-covalent interactions. You will be able to analyze various types of compounds which are associated with non-covalent interactions. Let us first of all understand what is supramolecular chemistry. Supramolecular chemistry is a highly interdisciplinary field of science covering the chemical, physical and biological features. They are the assemblies of organized chemical species and have greater complexity than individual molecules themselves. These assemblies are held together and organized by means of intramolecular, or we can say non-covalent binding interactions. In other words, supramolecular chemistry can also be defined as chemistry of molecular assemblies and intermolecular non-covalent interactions. Professor Jean Marie Lehn won the Nobel Prize in 1987 for his work in the area of supramolecular chemistry. He is also known as the father of supramolecular chemistry. The non-covalent interactions such as electrostatic interactions, hydrogen bonding and van der Waals forces define the intercomponent bond between the molecular individuals and populations. These non-covalent interactions are as important in supramolecular chemistry as covalent interactions in classical organic chemistry. The energy of these non-covalent interactions is much smaller than 200 to 400 kilojoules per mole, which is typical for covalent chemical bonds. In addition to relatively strong ion-ion electrostatic interactions, which is between 100 to 350 kilojoules per mole, and hydrogen bonding having an energy of 10 to 120 kilojoules per mole, they include much smaller London dispersion forces, or we can say ion induced dipole and dipole-dipole interactions, and these smaller, or we can say these much weaker forces, they lie in the range of 5 to 50 kilojoules per mole. Supramolecular chemistry covers the crystals, solutions and also the polymers in which non-covalent interactions play an important role. In general, supramolecular chemistry involves the self-assembly, that means the molecule itself assemble by these weak intermolecular forces to give you a bigger molecule, and that is why we call it a self-assembled molecules or a supramolecule. It also covers host gas systems. For example, your enzyme and substrate complexes is nothing but an example of supramolecule. These are held together by a variety of interactions, some of which are clearly non-covalent, example hydrogen bonds, and some of which possesses a significant covalent component, for example metal ligand interactions. It also has diversified enormously and includes now charge transfer complexes, inclusion complexes, for example cramps, hemicarcerins or cyclodextrins, mono and poly layers, micelles, vesicles, liquid crystals and co-crystals, they all consisting of at least two different kinds of molecules which form highly specific domains. You know, this is the best or most important feature of supramolecules. They form specific domains. The specificity and separateness of the charge transfer complexes and those of liquid crystals seem to be generally recognized. However, I can say the separate or the specificity of the separateness of these complexes like inclusion complexes or other molecular aggregates, the situation is not that clear. Now let us read about the non-covalent interactions and associated compounds. The supramolecular chemistry generally concerns about the non-covalent bonding interactions such as ion-ion interactions, ion dipole interactions, dipole-dipole interactions, hydrogen bonding, cation pi interactions, anion pi interactions, pi-pi interactions, closed shell interactions, van der Waals forces, crystal close packing and closed shell interactions. So these are all weak intermolecular forces which have a strength less than or which has an energy less than a pure covalent bond. However, not all these interactions are present in a supramolecule, but some of them. The term non-covalent encompasses an enormous range of attractive and repulsive effects. You can see the interactions that I have mentioned. The cation pi interactions, that is the interaction between a carbocation or any other cation with the pi electron cloud, it has to be an attractive interaction. However, on the other hand, anion pi interactions are repulsive forces. So we can say that the supramolecular or the non-covalent interaction, they can be either attractive or repulsive. The following figure compares molecular chemistry with supramolecular chemistry. As shown in the figure, we can see that in molecular chemistry, the properties we generally study are the chemical nature of the species, the shapes of the molecules, their redox properties, maybe their polarity, their magnetism, etc. However, in supramolecular assemblies or supramolecular chemistry, the properties we generally study are molecular recognition, the recognition capability of the host molecule, the catalysis, the transportation of ions, the degree of order, etc. The properties specific to molecular assemblies. You can see it is mentioned in the following figure. The specific characteristics of these supramolecules are recognition, catalysis and transport. And the properties we study are degree of order, interactions between subunits, symmetry of packing and intermolecular interactions. Now let us study some of the most common types of non-covalent interactions. Let us start with ion-ion interactions. The ion-ion interaction as an ionic cubic lattice, let us say for example sodium chloride, in which sodium ion is surrounded by 6 chloride anions and vice versa. The sodium cation is able to organize 6 complementary donor atoms about itself in order to maximize the non-covalent ion-ion interactions. The ionic cubic lattice of sodium chloride breaks down in solution because of solvation effects to give the species such as labile octahedral hexahydrosodium ion. The bond strength of ionic bonding is comparable in strength to covalent bonding, and the bond energy is in the range of 100 to 350 kilojoules per mole. The following figure shows you the ionic cubic lattice of sodium chloride, and in the next figure it is showing a supramolecular ion-ion interaction where there is an organic cation interacting with a simple anion, which is spherically shown in this figure. Now let us study what are ion dipole interactions. The bonding of an ion such as sodium with a polar molecule such as water is an example of ion dipole interaction, which has the energy in the range 50 to 200 kilojoules per mole. This kind of bonding is seen both in the solid state and in the solution. The ion dipole interactions in supramolecular structures of the complexes of alkali metals with macrocyclic ethers known as crown ethers is shown in the following figure. You can see that the ether oxygen atoms play the same role as that of the polar water molecules to stabilize the cation sitting inside the cavity. Although the complex is stabilized by the chelate effect, the effects of microcyclic pre-organization are also important. That means the cation which is sitting inside the cavity of these crown ether has to occupy a perfect space which makes it the best suitable guest molecule sitting inside its cavity. That's the effect of macrocyclic pre-organization. Apart from microcyclic reorganization, this complex or this supramolecular assembly is also stabilized by ion-dipole interactions. Now let us move on to dipole-dipole interactions. Alignment of one dipole with another can result in significant attractive interactions from matching of either a single pair of poles on adjacent molecules or the opposing alignment of one dipole with the other, as shown in the following figure. The energies for such interactions lie in the range of 5 to 50 kilojoules per mole. Given is the case of a ketone where the dipoles are so arranged that the negative end of one dipole comes closer to the positive end of the other dipole to show dipole-dipole interactions. Now, organic carbonyl compounds, they generally show this behavior. Well, in the solid state, and the calculations have suggested that this kind of interactions have an energy of 20 kilojoule per mole, which is comparable to a moderately strong hydrogen bond. The boiling point of ketones such as acetone, you can assume that the acetone must be having these dipole-dipole interactions among their molecules so as to enhance the boiling point of the ketones. Acetone boiling point is 56 degrees Celsius. However, it determines that dipole-dipole interaction of this type are relatively weak in solution. They are more pronounced in the solid state. Let us now study hydrogen bonding. This is the most important non-covalent interactions seen in supramolecular assemblies. A hydrogen bond may be regarded as a particular kind of dipole-dipole interaction in which a hydrogen atom attached to an electronegative atom or electron withdrawing group is attracted to a neighboring dipole on an adjacent molecule or a functional group within the same molecule. Hydrogen bonds are commonly written as electronegative element bonded to hydrogen, and this is attracted to another electronegative element, and usually involve a hydrogen atom attached to an electronegative atom such as oxygen or nitrogen as donor, and a similarly electronegative atom often bearing a lone pair as an acceptor. The typical range for hydrogen bond strength is from 10 to 120 kilojoules per mole, and the typically hydrogen bonded OO distances are 2.5 to 2.8 angstrom in length, though the interactions in excess of 3 angstrom may also be significant. An excellent example of hydrogen bonding in supramolecular chemistry is the formation of carboxylic acid dimers. Figure shows that the shift of frequency of hydroxide in IR stretching from 3400 centimeter to 2500 centimeter inverse is accompanied by a significant broadening and intensifying of the absorption. The reason for this is hydrogen bond formation. Hydrogen bonds are ubiquitous in supramolecular chemistry. In particular, hydrogen bonds are responsible for the overall shape of many proteins, and they are also the reason of recognition of substrates by numerous enzymes, along with the pi-pi stacking interactions, and also for the double helical structure of DNA. The following figure has been shown on your screen shows supramolecular hydrogen bonding interactions in carboxylic acid dimers. The figure B shows organic molecule, and figure C and D shows guanidine and cytosine base pairs of DNA. Now let's move on to the other non-covalent interactions known as pi-pi interactions. These are generally observed when especially you have benzene rings in your molecular structure. The pi-pi interactions occur between aromatic rings. So sometimes it is also called aromatic pi-pi stacking interactions. Often in situations where one is relatively electron rich and one is electron pair, this kind of interactions is observed. The typical range for pi-pi interaction strength is from 50 to 500 kilojoules per mole, and there are two types of pi interactions. One is face to face other one is edge to edge, as shown in the figure. The face-to-face pi stacking interactions are responsible for the slippery feel of graphite and its useful lubricant properties. Similar pi stacking interactions between the aryl rings of nucleobase pairs also help to stabilize the DNA double helical structure. The edge-to-face interactions may be regarded as weak form of hydrogen bonds between slightly electron deficient hydrogen atoms of one aromatic ring and the electron rich pi cloud of another. Strictly, they should not be referred to as pi stackings since there is no stacking of the pi electron surfaces. The edge-to-face interactions are responsible for characteristic herringbone packing, similar to the letter T, one over the other, in the crystal structures of a range of small aromatic hydrocarbons, including benzene. Such kind of pi-pi interactions becomes very important in a larger supramolecular assemblies where the aromatic rings forms the major part of the host molecule, and they lead to special stabilization to these supramolecular assemblies. Now move on to another kind of interactions called cation pi interactions. The transition metal cation such as iron 2+, Pt2+, etc., they are all well known to form complexes with olefinic and aromatic compounds such as Zisel salt. Zisel salt is trichloroethyl platinate and ferrocene. This is a very popular common molecule wherein iron 2 is sandwiched between two cyclopentenyl rings. The bonding in such complexes is strong and could by no means be considered non-covalent, since it is intimately linked with partially occupied d orbitals of the metals. Even species such as silver with benzene have a significant covalent component. The interaction of alkaline and alkaline earth metal cations with carbon-carbon double bonds is, however, a much more non-covalent interactions and is suggested to play an important role in biological systems. For example, the interaction energy of potassium and benzene in the gas phase is approximately 80 kilojoules per mole, as shown in the figure. By comparison, the association of potassium with a single water molecule is similar at 75 kilojoules per mole. The reason for this is that the potassium ion is more soluble in water than in benzene and is related to the fact that many water molecules can interact with potassium ion, whereas only a few bulkier benzene molecules can fit around it. The interaction of non-metallic cations such as ammonium cations with double bonds may be thought of as form of XH pi hydrogen bond. Let us now study anion pi interactions. Cation pi interactions are favorable. However, the interaction of an anion with pi electron density seems like it should be repulsive. And indeed, the affinity of the aromatic ring containing the cryptand, which is shown in the figure, for halides rapidly falls off in the order fluorine to chlorine to bromide to iodide. And this is because of the anion pi repulsions in case of the larger halides. Iodide, being the larger halide, comes closer to the benzene nucleus, and hence the anion pi repulsions makes it unstable. All these anions, they do not form very stable complexes except the fluoride ion, which shows a constant anion ring centroid distance of 3.7 angstrom. However, there is a charge difference between an overall neutral aromatic ring and an anion, and therefore in principle the possibility exists for an electrostatic attraction. Such kind of short anion pi interactions have been noted for organometallic calixarine derivatives, which is shown in the following figure, where the aromatic ring bears a significant positive charge because of the binding of ruthenium ion between them. So in this organometallic calixarene, if an anion is incorporated into the cavity, these anion pi interactions will be implicated as the controlling elements in the self-assembly reactions. Now silver 1 complexes with pi acidic aromatic rings have also been noted to show these anion pi interactions. That means these anion pi interactions can be repulsive as well as attractive depending on the nature of benzene nucleus attached to these self-assemblies. Now let us study the van der Waals forces and the crystal close packing. Van der Waals interactions arise from the polarization of an electron cloud by the proximity of an adjacent nucleus, resulting in a weak electrostatic attraction. The typical range for van der Waals interaction strength is from 0.5 to 40 kilojoules per mole. These van der Waals interactions are non-directional and hence possesses only limited scope in the design of specific host for selective complexation of particular guests. In general, van der Waals interactions provide a general attractive interaction for the most soft, that is most polarizable species with the interaction energy proportional to the surface area of the contact. In supramolecular chemistry, they are the most important in the formation of inclusion complexes in which the small, typically organic molecules are loosely incorporated within the crystalline lattices or molecular cavities. For example, the inclusion of toluene within the molecular cavity of para-tertiary-butyl phenol based macrocycle and para-tertiary-butyl calyx fluorine as shown in the following figure. As you can see, this figure has the cavity absolutely fine for toluene and these van der Waals interactions can stabilize this. The shown figure is nothing but an extracrystal structure of these typical van der Waals inclusion complexes of para-tertiary-butyl calyx fluorines. The other side of the figure shows the hydrophobic van der Waals interactions. For molecular assemblies in solid state, the crystal close packing effects determines the structural organization and the supramolecular motifs. Hydrophobic interactions, they also play an important role in supramolecular chemistry. These interactions are responsible for replacing the water molecules within the cavity of a host by an organic guest molecule as shown in the figure. The displacement of water molecule is shown by the incoming guest molecule and it is stabilized by hydrophobic effect, and this leads to the enthalpic stabilization. Let us study what do we mean by closed shell interactions. Atoms with unfilled electron shells form strong covalent bonds. Ions generally have close valence electron shells but experience strong attractions between oppositely charged pairs. One would not intuitively expect closed shell atoms of neutral or like charges to form significant interactions. However, in some cases they do. These interactions are termed as closed shell interactions and they include secondary bonding interactions or metallophilic interactions and halogen bonding. Closed shell interactions are broadly comparable in strength with moderate strength hydrogen bonds and are thought to arise from electron correlation effects, significantly strengthened by relativistic effects in heavy metals, particularly gold, where they are termed as orophilic interactions. The closed shell interactions are most pronounced for heavy metals, with examples reported for electron configurations from D8 to D10S2, and the heavier halogens with halogen bonding strength decreasing in the order iodide to bromide to chloride to fluoride. Now let us summarize what kind of all non-covalent interactions we have studied and what is supramolecular chemistry. So in this module, what we have understood is that supramolecular chemistry is a highly interdisciplinary field of science covering the chemical, physical and biological features of the organized chemical species of greater complexity than the single molecules themselves, which are held together and organized by means of intermolecular non-covalent binding interactions. The energy of these non-covalent interactions is much smaller than 200 to 400 kilojoules per mole, which is typical for covalent chemical bonds. In addition to relatively strong ion-ion electrostatic interactions of the order 100 to 350 kilojoules per mole and the hydrogen bonding of the order 10 to 120 kilojoules per mole, they include much smaller London dispersion forces, ion-induced dipole forces, dipole-dipole interactions that are in the range of 5 to 50 kilojoules per mole. The supramolecular chemistry generally concerns non-covalent bonding interactions such as ion-ion interactions, ion-dipole interactions, dipole-dipole interactions, hydrogen bonding, cation-pi interactions, anion-pi interactions, pi-pi interactions, closed shell interactions, van der Waals forces and crystal close packing as well as closed shell interactions. The term non-covalent encompasses an enormous range of attractive as well as repulsive effects.